Afternoon. I want to talk about the binomial theorem, that's Newton's, and then the general nomial theorem, that's mine, okay? In other words, it doesn't have to stop with bi, and it can be a pattern of any shape that you want, okay? Now, what good is the binomial theorem? Well, in the old days, people didn't have calculators. Suppose you wanted to work out something like that. Without a calculator, that's a big job, actually. So the binomial theorem allows you to get a pretty good approximation without working all the details to a few decimal places. And I'll show you why that's the case in a minute. But what about if we had something like this? Okay, my general nomial theorem, trinomial, tetranomial theorem will allow you to work out that one pretty close as well. So we'll show you how to do that. But we learn a little bit about. Now, I'm not going to teach you about combinations and permutations. Go and look that up yourself if you want to. But I will give you an insight into how this whole thing is going to work, okay? I'll teach you something first. And then I'll just launch straight into the practicality of the calculation, and I'll keep it dead simple. I know you guys have probably learned the binomial theorem in school, and you couldn't remember it, okay? This you will remember. It's dead easy. Okay, and you can generalize it any way you want. I don't know why people don't teach this. I think people probably didn't realize that this system kind of works. Maybe you will spread the word around that this is the way to go, so that, you know, people in schools and colleges can learn this and teach it to their students. Normally I don't like sharing information, but you see, not everybody hits on my stuff. I know that only a few elite and interested people hit the talks that I put out on YouTube, all right? Esoteric knowledge is not for the masses. I always say, don't spread it around, keep it to yourselves, right? I always feel like a kind of a sage or a sorcerer. They don't want to share their knowledge too much. A little bit though. You know, it's nice to have an apprentice. So, if you want to be an apprentice, feel free to email me at droreilly@physicist.net, and I will teach you stuff that I'm not prepared to share in public, okay? This one I'm going to share. Alright, so we'll begin with just, we're not using the word permutation and combination, because actually I'm not sure, because it looks to me like it's exactly the opposite to what people teach you in the books, so I'm just going to tell you something. Suppose we have the letters A, B, C, and D, and we want to rearrange them in 4 boxes. In other words, how many different words can we make using these letters? Well, I can put A, B, C, D. If I put a letter in the first box, it leaves me 3 to put in the second, 2 in the third, and 1 in the fourth. The answer is 4 factorial ways. Twelve times 2 is 24. So, let's count them. Well, I could put A first, and then I could go B, C, D. B, C, D. See what's happening? The D is hopping over a step every time. B, C, D, B, C, D, B, C, D. Now I reverse this permutation. I go B, D, C, B, D, C, B, D, C. And there are all the ways I can do it with an A at the front. A at the front. I could swap it now and put a B on the front, put the A in here, and do the exact same thing. So that's 6, and another 6. And I could do it again for the C in front. That's another 6, that's 3 6s, and a fourth 6. 4 6s, 24, right? Or 4 factorial if you like, it works. But this is another way of looking at it. So, that's the way it is when I have different letters everywhere. But now I'm going to make 2 of them the same. The first 2 letters are A and A. I'm going to have less choices. I can make less words. Right? Because 2 A's are going to get reversed. AA and AA, when you reverse them, it's the same thing. Alright? CAAT and CAAT with the 2 letters is still cat. CAAT. Pronounced cat. But you reverse the 2 A's, it's still the same word, but written the same way. The order doesn't matter, kind of. So, in this case here, I can start by putting in A first. If I put in A first, I have 1, 2, 3, 4, 5, 6 different ways. A, B, C. The same kind of permutation, A, B, C, A, B, C. Reverse the C and the B and shift the A across gradually. See, the A is shifting, the A is shifting. Like over here, the B is shifting, the B is shifting, right? So, 1, 2, 3, 4, 5, 6. Now I can come across and put the B in the front. But wait a minute, now I've got two A's, so I don't have as many choices. I can have AAC, ACA, and ACA. That's it. For the C in front, I can go AAB. I could have put it the other way, AAB and AAB. I should have put it the other way around, doesn't matter. One way or another, there's 6 there, but only 3 here and only 3 here. Okay? 6 and 3 is, wait a minute, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 ways altogether. But how can I write the 12 systematically? I can go to 4 factorial, but cut out the 2 choices that are going to be the same all the time. 2 letters, 2 factorial, right? Now if 3 letters were the same, it would be over 3 factorial, and that's the way it works. I'm going to do a general word. I forget how to spell Mississippi. Mississippi? I'll do Navan first. Navan is a town near me in Ireland, and Pierce Brosnan comes from Navan. So, Pierce Brosnan went to London at the same time I went to London. Except that he became a film star and I worked in construction, right? Well, he's 6'3" and I'm 5'7". I'm as good looking. I was as good looking as him. Doesn't matter about that. I wish him well. Pierce Brosnan, what did he play in? Remington Steele, I guess, was his early TV shows. And then he was James Bond. But he did a good film one time that I liked, In the Snow. He's quite a good actor, actually, with Liam Neeson. I like that one. I forget what it was called, up in Alaska somewhere. Never mind, that's the system. So we're going to give you a general rule. This is the town that Pierce Brosnan comes from. It's just down the road from me. So, I have 1, 2, 3, 4, 5. How many different rearrangements can I make using these letters? Well, I've got 2 letters repeated, so I put 2 factorial. I've got 2 n's repeated, and another 2 factorial. So it's 5 times 4 times 3 times 2 times 1. That's how you do a factorial. 2 times 1 is a 2 factorial. Whoops. So that cancels, and a 2 goes into there too, so it's 5 times 2 times 3, which is 10 times 3, which is 30. So I can make 30 different rearrangements of this, or make 30 different words using those letters. All right? If they were all different, if they were all like the same, it would be a much larger number. Okay? Let's do Mississippi. Now, how do you spell Mississippi? I don't know. I'll do some word that sounds like Mississippi, the place, and I'll put lots of letters in it. Well, Mississippi goes from M-I-S-S-I, Missis, I-P-P-I. Okay, how many different rearrangements can I make using these letters? Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's going to be 11. In other words, the number of, I'm not saying if they're permutations, combinations, I'm just saying how many different words can we make. Over, well, there's 4 i's. 1, 2, 3, 4 i's. So we go 4 factorial for the i's. 1, 2, 3, 4. 4 factorial for the s's, and 2 factorial for the p's. That's the answer. Okay, so I go get rid of these and cancel those. 2 cancels with that to get a 3. 3 cancels with that to get a 1. 4 cancels with that to get a 2. 2 cancels with that to get a 1. So I'm left with so whatever that is, I'm not going to work it out. I could. Could be that, but I'm not sure. I might have made a mistake here. Doesn't matter, you can check that on your calculator. Mississippi, the number of ways to rearrange Mississippi. Now I'm going to use this way of counting in the binomial theorem. Now for those people who did the binomial theorem at school, you probably used Pascal's triangle. We build up Pascal's triangle, they turn out to be the binomial coefficients. Take these two, take those two, take those two. So we take these two and I get 1 times 3, sorry. Is it adding? Yeah. And you build it all up. These are the binomial coefficients. And where do they crop up? They crop up in this expansion. Okay, take away the brackets and use distribution. And look what's happening. I'm getting arrangements of letters. In many different ways can we arrange the A and the B's, 2's. In many different ways can we arrange the letters A and B and B. These are the binomial coefficients on this row. Now anything to the power of 1 is 0, so that's the first row. That anything to the power of 1 is itself. Anything squared will have these coefficients. They're the binomial coefficients, okay? Now there is a way to do it using, well, I'm canning that. I don't want to do it. Let's do a plus b cubed. Well, it's a plus b times this thing. So I go a times this object. And b times this object. Now look at what we're doing. We're just doing the same thing for each particular case. We're making, how many different words can we make using A, and B? Well, there's one there, there's one there, and there's one there. 3. How many different words can we make using A, B, and B? There's one there, there's one there, and there's one there. So we get one way to arrange A, and A. In other words, 1 times A cubed. 3 ways to go AAB. In other words, a squared times b to the power of 1. 3 ways to do b squared a. And that's it. And these are the coefficients on this row here. Now I could go and multiply a plus b. And I would do the exact same thing, and I would get all these coefficients on the fourth row. A plus b to the power of 5, and so on and so forth. This is the binomial theorem. But I'm going to tell you this, that the way to do any situation is use the Navin, Mississippi principle, right? Find out the number of words you can make using those mixture of letters. So if we're only doing a binomial, that's two numbers, and it's squared and cubed in any power you want. So let's get rid of that. Let's do this one. Now, for this expansion here, we're going to have, as before, a to the power of 6 plus a to the power of 5, b to the power of 1, plus a to the power of 4, b to the power of 2. And a to the power of 0, b to the power of 6, because b to the power of 0 exists there, I just didn't write it down. Now the question is, what is the coefficient for every one of these objects here? Okay, what is the coefficient? I'm going to tell you. The coefficient for a to the power of 4, b squared. Now notice that the powers, 5 and 1 is 6, 4 and 2 is 6. 3 and 3 is 6, 2 and 4, 1 and 5. The coefficients, the exponents always add up to 6. Well, 4 and 2 is 6 factorial. So 6 factorial over 4 factorial, because this looks like this. It's a word with 6 letters, but 2 of them are repeated. This is repeated 4 times, this is repeated twice. That is the coefficient of this guy there. So they cancel. 2 cancels with that 3. The answer is 15 is the coefficient for that one in there. Now you can do any one you want. You can go and fill in all the blanks if you want. Yeah? The coefficient of this one here is 6 factorial over 2 factorial, 4 factorial. The coefficient here is 6 factorial over 5 factorial, 1 factorial, 6 factorial, and so on and so forth. You can put them all in. Dead simple, right? Now you know how to do the binomial theorem. At least put it into practice. You can go and look up permutations if you want to. Now we can do some examples with numbers if you want. But I'll do that in a minute because I may not have enough time. I want to show you a more general case. Suppose we have A plus B plus C to the power of 4. All right, that could be tricky. And this 4 could be 12, right? It's going to be like this. Well, we're going to have a to the power of 0 and these two to the power of 1 and 3. A to the power of 0, 2 and 2. A to the power of 0, 3 and 1. And something like that, I guess. Did I miss one? I should take this one. Plus as well, okay? Now I go through all the next plus. I could go a to the power of 1 and do all the permutations of coefficients for the next one. And I could go a to the power of 2 and all the coefficients thereafter, making sure that the numbers at the top add up to our particular number up here. 1 and 3 and 0 is 4, 2 and 2 is 4, 3 and 1 is 4, 4 and 0 is 4, and so on and so forth, right? Now we need to know what the coefficients are. Let's do the coefficients of this one. We can do the coefficients of any one, but the coefficient of this one here is going to be 4 factorial over 3 factorial. 0 factorial you can put in if you want, because 0 factorial is defined to be 1. You don't have to put it in. Well, 4 factorial over 3 factorial is just 4 itself, so that the coefficient of this one here would be 4. Right? Dead easy. Let's do another one. I could work in all of it. You'd be covering up the board with all the examples. I'm giving you term by term example. Get your head around that. How about that? Okay, let's see what we would get. Now you go through all the different possible powers, making all the different selections. I'm not going to write them all down, but I'll just do this one. What is the coefficient of this particular term here? Well, it's going to be 12 factorial, because this looks like this. That's the answer, okay? Which is kind of weird. Maybe I made a mistake there, did I? I guess not. If that's what it's telling me, that's what it has to be. All right, so then you can go and experiment with that on your own. Oh, let's do one example first. Oh, by the way, I should add, you can go into a proof and show that negative exponents and fractions work. We'll do this one. Now this is going to be the B. And A plus B to the power of 6 is going to be 1 to the power of 6, 0.02 to the power of 0. And the next term. And so on and so forth, right? Now we need coefficients. And what are they? Well, 1 to the 6 is always the same. 1 to the power of 6 is 1. We need a coefficient for this one. Now, 1 to the 5th is still 1, but 0.0 to the power of 1 is what we've got there. 1 is the same, but we need a coefficient. What are the coefficients? Well, it's going to be 6 factorial for this one. 6 factorial over 5 factorial is 6. Okay? Now for this one here, it's going to be 6 factorial over 4 factorial times 2 factorial. Now those 4's cancel very quickly, and the 2 cancels with that, and I get a 3 times 5, so that the coefficient in there is 15. So, 15.08. What did I get? And you can work it out on your calculator, because what happens is this. Successively smaller terms get less and less and less. That's it. Okay, so you generalize the binomial theorem. Newton was a great guy, but so am I.